bringing together all of chapter 7 today. No, there's not cards to choose today because we're kind of tight in this room. Everybody shows up, which I know everybody won't. But here is a place to start with those that you chose to sit next to or near. See if you can work your way through these ideas, these 6 questions. And we'll come back together in a minute and go through some solutions. We're going to be accessing that applet page. So if you don't already have that pulled up, if you had it bookmarked, find it and pull it up. Or if you have a graphing calculator, using that as well. So get going on this. And while you're doing that, I'll take attendance. So again, what that was going, the mean of the sums is the mean of just any individual from the sample times the 39 that are sampled. So the sum, the average of the sums would be this number. The sum of the ages would be this number. That would be my expected sum of 39 individuals, would be 39 times 35. Standard deviation is the square root of the sample size, n, times the standard deviation. 62 point here. So there we go. All right. Next up is number 29. And that is, where are you? Amy. Number 2, please.
Is it because the sample size is over 30?
So n is 39, which is over 30. And then what's my resource? What allows me to say this? The most important aspect in all of entry-level statistics. Do you remember the letters? Anybody near you remember the letters or the name?
CLT.
The CLT.
Oh, yeah,
The CLT is the central limit theorem. So when a question asks, what is the distribution? A way that you would write this out, likely as a full sentence. The distribution of sums will be normal because the sample size is over 30, and the central limit theorem tells us that when sample sizes are over 30, the sampling distribution is normal. At which point you're saying that was a lot to say. Yes, it is. So, have your hand warmed up come the next exam time, because it's going to be sentences. Being able to articulate whys and hows of things. Hopefully you're learning too, using all these applets online. Calculation, going to be just limited to what you plug into your computer and it kicks out an answer. You need to be able to explain how you got there and then what it means. All right. Moving on to number 3. Person number, lucky number 13 in the class. Joel. The mean of the averages, or the mean of the X bars, is 35. The mean, and then the standard deviation of the averages. No. It is not 10. How did you get 1.6 aside from hearing someone across the room shout it out to you?
Why didn't you do the 35 square?
Sigma over the square root of n. Remember, for the sums, it was square root of n times sigma. For just the average, it's sigma divided by the square root of n. And what was that number we think? 1.6 is what someone else said. Any bobbleheads in the room going to confirm that number? Yes, I got bobbleheads and a hand raised. I've not heard an amen, but we'll go with that. There we go. And now, next number. Where was I? Next person is absent. Next on the alphabet is Nick. Nick, what is the distribution?
We said that we got a normal distribution.
So pretend it's exam time based on what we talked just in the last one. What would you have to say?
I have no clue.
That would not be a good answer. What's my reason for normality?
We said that since we're calculating the average, the distribution would also be normal if the sample size is large enough. Central limit theorem.
Central limit theorem, if the sample size is large enough, and we say that's anything over 30, 39 is over 30, so our sample size is large enough by the central limit theorem to say, ready for this? To say that the sampling distribution of averages is normally distributed. Yeah. So not only what the distribution is in terms of shape, but what is it of? It is the distribution of sample averages. Or you could say the sampling distribution of averages. They are the same thing. So the distribution of sample averages or the sampling distribution of averages will be normal because the sample size is 39, which is large enough because of the central limit theorem to indicate that it is a normal sampling distribution. All right. And then I've seen many people online grabbing the applet, plugging in those numbers. What we'd be looking for in a case like this for number 5, 1, did you draw a picture? 2, do you have the correct boundary points labeled on that picture? Oh, and a correctly drawn picture would be a normal distribution centered at 35 with 3 standard deviations to the left, 3 to the right, and at least one of them labeled accordingly. So if you had the mean at 35 labeled, one above you that's 45. And then you have your boundary points of 35.9 and 38.5 labeled on your picture. And then showing the work of how you got there. I could ask, and don't be surprised if I ask on exams, in the process, indicate what your 2 z-scores were. Or indicate the areas of the 2 tails that helped get you to this answer. Or some other specific aspect as opposed to just the answer. But ultimately then, teeny tiny little picture here. $35, $45, 1, 2. I'm from 38, which is somewhere here. 35.9, just barely above 35. That's what I'm finding. The probability that 35.9 less than X bar less than, oh, it's not, it's the average ages. Sorry about that. My standard deviation in this case is not 10, it's that number there, 1.6. I have to read my own question. So that above point is 35 or 36.6. Because I'm talking about the average ages, not just ages. So the average ages, I'll start afresh down here. That was a terrible curve. Still centered at 35. But now, 1, 2, 3. One standard deviation is 1.6. So this is 36.6. Nope. I'm going to move everything up here just a little bit. 36.6. So then when I'm at 35.9, I'll be somewhere here to about somewhere here, finding an area. $38.5. Did anybody find that actual percentage? Yes, what is that number?
I think it's 17.2%.
That seems low to me.
I got 25.45%.
So when you did this, if you all have your applet open, go. If not, go there now. We're going to choose the normal applet. LMN. Normal. You can actually put in the mean of 35. Standard deviation of 1.6. Now, is it 1.6 exactly, or is it 1.6 rounded? 1.6 rounded. What would it be? Give me like a couple, 3 decimals to it. 1.601. I'm going to put my sigma in the computer as 1.601. All right. Most everything you're going to have from me with the online quiz, if you read your email from me earlier today, as well as on the exam, will be pretty much to the nearest 10,000th. So 4 decimal places most of the time. So 1.601 or 6.01 or 1.6012, either would be fine at that point. The boundary point then of my first one will be 35.9. And the area above X bar is greater than 35.9, according to the online applet, when I plug in that info, is 0.28701. And then I change the X value, instead of 35.9, I change it to 38.5. So the probability that X bar is greater than 38.5 is 0.0144. This area here corresponds to this area out there on the end. This area here would be the entire area of the entire end. So my desired area of red would be this whole area in yellow, 0.28711. Sorry about the little red marks in there. And then I'm going to subtract away the green because that's what's above 38. I only want from 35.9 up to 38.5. So this number minus that number should give me the correct value, which this is probably closer, but if you rounded and had 1.6, that would be the difference. If I just subtract this, I get 0.272 something. So 27%. And that would be the probability. So then a final answer would be something along the lines of, there is a 27 point, whatever number we got, percent chance, 27 point something percent chance that a random sample of 39 would have an average age between 35.9 and 38.5. So once again, if a random sample of 39 people were selected from this population, there's approximately a 27 point, whatever it was, 27 point something percent chance that the average age of that sample will be between 35.9 and 38.5. A good habit is, even if the question does not ask for an interpretation of the value, you should provide it anyways. I'll be asking for it. Calculate the z-score, interpret what it means. Find the probability, explain what that means. And then 90th percentile for the sums. Oh, I moved up too far. What was the the mean of the sums was 1365. 1, 2, 3, 1, 2, 3. 1365 is my 50th percentile. The 90th percentile will be somewhere up 10% at the end, right about here. How do I know that? Using the empirical rule. This area down here is 90%. And then if I use that online tool, we're back to the applet. So if you have that open, for the mean, put in 1365. The standard deviation, what was that number? 62 point, was that 45? 62.45. And then in the red box, or salmon colored or whatever that is, if I put 0.9 for 90% and then have it set to less than, it will give me the X value of 1445.0329, which means, interpreting, if I selected randomly 39 individuals, I would expect the sum of their ages, I would expect 90% of all possible sums of ages to be 1445 or less. Another way to say that is, if I randomly selected 39 people and found that the sum of the ages was 1445, 90% of the sums are below them. Because that would also include the correct interpretation of a 90th percentile. And then lastly, as part of our intro, number 7, what are the mean and standard deviations of the age of tablet users? Well, the mean was 35 and the standard deviation was 10. What is the distribution? We don't know. So all of these up here are for a reason to get us used to reading the language. What are the mean and standard deviation of the sums? What are the mean and standard deviation of the average age? What are the mean and standard deviation of the age? Just the age is that parent population with an average of 35 and a standard deviation of 10. But as we talked earlier, when there's no designation for the shape, it's unknown. We cannot say anything about the shape of the distribution. We have no idea if the ages are mound-shaped, skewed in any way, bimodal or multimodal, uniform. We have no idea. So if 7 then asked us to find a probability, we would say we cannot find a probability because we don't know the shape of the distribution. Well, sort of new stuff. Law of large numbers. If my sample size increases, the sample average will approach what, everybody? If my sample size increases, the sample average will approach the true average. The true average, sometimes called the population average. Population average. We could say mu. For those of you that like calculus and pre-calculus, the limit as n approaches infinity of x bar is mu. As my sample size increases, x bar will approach mu. The larger the sample size gets, the closer the standard deviation of the sample gets to the standard deviation of the population. Same idea. As n approaches infinity of sigma sub x bar will approach, not sigma sub x bar, sigma sub, let me fix that, s of x will approach sigma of x. Difference here, this says the averages, this just says the standard deviation of the sample. This is jogging our memories, trying to remember what connects to what. As far as study tools, right? You've got all these different distributions we've talked about. They all have all their different little values that go with it. If you're a flashcard maker, Quizlet maker, something to remember what goes with what, which, where. Becomes a matching kind of game. Is there anything up there that looks familiar to anybody? Let's see, this is part of a uniform distribution. The average of the uniform distribution is the maximum plus the minimum divided by 2. It's the average, the middle spot.
Normal distribution would be mu x bar is equal to mu x.
Normal distribution, mu of x bar will equal mu of x. Nope, we're actually going to take that back and say that's a sampling distribution. The average of all the averages equals the average in a sampling distribution. I see I'm missing, this should be a square root. What else am I missing in there? This is a giant square root. Exponential. The average, and that's my decay constant. Our book, I think, actually writes it the other way around. They say m equals 1 over mu. It's the same thing. This is the Poisson distribution. This is the standard deviation of a normal curve. It's actually a standard deviation of anything, but a normal curve works that too. Exponential, mu and sigma are the same. Uniform distribution, that is the standard deviation of a uniform distribution. This is the equation of an exponential distribution. Sampling distribution, the standard deviation of all the averages is equal to sigma x over root n. I know, it's a big mess right there. It's all being recorded, so you can go back and look at that later. Important because now we're going to start taking one of those and overlaying it into a normal distribution scenario. So here's what we got. Suppose that market research analysis for a cell phone company conducts a study of their customers who exceed the time allowance included in their basic cell phone contract. For those of us who for many years did not have unlimited data, you got capped at a certain number of minutes, certain amount of data, that kind of thing. The analyst finds that those people who exceed the time included in their basic contract, the excess time used follows an exponential distribution. So the minute that happens, you're thinking, what are my formulas and concepts related to an exponential distribution? All right. So we're going to start with the shape of an exponential distribution, which is down here. An exponential distribution goes like this. Starts right there. All right. The mean of that, it tells me actually in the writing, it says with a mean of 22 minutes. So my mean is 22. looking at those formulas that we had on the previous sheet, sigma is the same as mu in a geometric, in an exponential. So sigma is also 22 minutes. So my mean is somewhere right about here at 22. And don't forget also the applet can do exponential functions. So if I had to find, and we'll do that on the next sheet, I think I'm going to ask you to find the probability that x is greater than 20, I think is what I said. All right. So we'll come back and need to remember those numbers, and we'll find that value. But then it says, consider a random sample of 80 customers. Wow, immediately I need to be thinking 80 is a big number. It's over 30, and that's an important value. So my n is 80, which is over 30. So I'm going to consider this random sample of those who exceed the allowed time. We're going to let x equal the individual cell phone customer who exceeds his contract time. So then below, what is the mean and standard deviation of the sampling distribution? The mean of all x bars is equal to the mean of x, which will be 22. The standard deviation of x bars is equal to the standard deviation of x divided by the square root of n, which equals 22 over the square root of 80. And what's the shape? Since n equals 80 is greater than 30, the CLT, central limit theorem, allows us to assume sampling distribution of averages, or of average, is it average overages? Average time is approximately normal. And we say approximately because everything, it's like saying, making a universal statement about an approximation. All of them will be approximately normal. There isn't really anything as calling something exactly normal because it's all based on sampling data anyways. So sampling is always an approximation of an actual population. The only way we can ever say exactly is if we had the whole population, well then the whole field of statistics actually wouldn't exist. $80. So there it is. Find the probability. There's my exponential. Here's 20. That x is greater than 20. Do you have your applet open? Go to the applets. There's the website at the top if you don't remember it. If you haven't bookmarked it, there it is. And in the list of all of those applets, we're looking for exponential. exp.html. And in there, it asks for a lambda and an x. Lambda, recall, our book calls m. All right, lambda and m, that is the decay coefficient. Mu equals 1 over m. Another way to say it, m equals 1 over mu. So in the lambda box, I'm going to put 1 over 20. That's my decay constant. So I go 1 divided by 20. And after I do that, it should show your graph for you of what it looks like. My boundary point that I'm looking for is 20, so that's what I put in here. Oh, sorry. This should be 22. Isn't that the mean? This right here is 22. This is 20. That's my boundary point. And then it tells me that this area in that curve is 0.40289. And then I would write a sentence saying, if an individual who exceeds their time limit is randomly selected, there is a 40.29% chance that they exceeded 20 minutes. So again, if an individual is selected from those who exceed their allotted time, randomly selected, there's a 40.29% chance that they exceeded 20 minutes. Finding the probability of the averages. We said from the previous page, we've already justified it, not going to rewrite it, follows a normal curve. The average is also 22. So x bars follows a normal curve, 22, and my standard deviation is 22 over the square root of, what was my sample size? 80. And 22 divided by the square root of 80 is 2.4596. So this will be 24.4597. Let's go like that. I've got 2 points labeled on there. Again, because this is approximately 2.4597. So where is 20? 20 is somewhere right about here. So now we go back to our applets page. Which distribution are we choosing? Normal, because we've determined it's a normal distribution. My mean is 22. My standard deviation, 2.45967. That's all the decimals I really need. Now I want to find out the likelihood that my average is greater than 20. This area all up here. Oh, I already got my there. Run it through my my computer, 0.79192. So while an individual only has a 40% chance of being randomly selected and having a value greater than 20, there is a 79.192% chance that a group of 80 people will have an average over 20. So this is ending where we are in chapter 7, where we're looking at these distributions. Where we go to in chapter 8 is we're going to then start looking at, okay, what if I don't know mu? And I don't know sigma? Can I use statistics to find what they actually are? Chapter 7 is kind of like living this ideal world where we know mu. In most cases, especially if you start getting into anything that does research, you're not going to know mu. You're not going to know the average anything. So you're going to be doing designed experiments and studies and investigations and doing a sample, and you go, okay, here's my X bar. And then assuming you did proper technique, your X bar should be close to mu, but it's not exactly mu. So then we're going to create intervals to estimate where mu actually is. Now, if I want a really, 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 really wide interval, think about it for those of you who do fishing. If I have a big net, bigger chance I'm going to catch the fish. So if I have a really wide interval, I'm going to have a higher likelihood of capturing the actual mean. But if it's a really wide interval, it loses sometimes its authority. I mean, you can make any interval you want, but then say, but that's such a wide interval. Like, if the average could be anywhere in that interval, that doesn't help us much. So we're going to do some techniques and some talking about what are called building confidence intervals. And in doing so, we'll do that for when we know sigma, which we rarely know. And then we'll go to when we don't know sigma. And then we'll do it for proportions. And if memory serves me right, we'll have M&Ms in class on Monday to do proportions as well. If not Wednesday, or Monday, then it's Wednesday. So if you don't eat chocolate, don't eat them. But that's all I got for today. Until next time.